In classical physics, or Newtonian physics, as it is often called to honor Sir Isaac Newton, who formulated its most important laws, the universe was believed to be mechanical, like a big clock. It was thought that everything was predictable, just as we can predict exactly where every ball on this pool table will stop if we know the direction and force of the cue ball and the position of all the other balls. Today, we have a much different vision of our physical world. We now know that we live in a dynamic universe and that some things will always remain unpredictable and unknowable. This program sketches in the history of modern physics and explains the cosmic shift in our understanding of the universe. By the end of the 19th century, classical physics had made outstanding achievements. Newton had explained how the planets are held in their orbits by the force of gravity, and Maxwell showed how light was transmitted by electromagnetic waves. The universe was assumed to be stable, unchanging, and in principle, predictable. Soon, it was believed, scientific laws would explain everything, even human behavior. But around the year 1900, physicists began noticing certain anomalies. Technical improvements made it possible to make better observations, and an increasing number of things were observed that could not be explained by existing theory. The motion of things at the subatomic levels and at velocities close to the speed of light did not obey the laws of classical physics. Out of this crisis has come quantum mechanics, which radically changed physics. It had long been believed, by some, that matter was made up of tiny particles. The ancient Greeks called them atoms. In the early part of the 19th century, John Dalton, an English schoolteacher, developed on this idea, but he believed that atoms were static, like tiny buttons. It was not until 1897 that J.J. Thomson discovered electrons. And soon after, Ernest Rutherford identified the nucleus of atoms. These discoveries increased efforts to understand the structure of the atom. At the beginning of the 20th century, physicists refined these models as they discovered more about the behavior of electrons. It was found that electrons moved around the atom at different distances from the nucleus, corresponding to higher or lower energy levels. The electrons could gain or lose energy, making them jump up or down steps, like those on a staircase, but only in whole steps, nothing in between. The energy was emitted or absorbed as light and seemed to be in packets. Max Planck called these packets of energy quanta. The movement of the electrons did not follow the laws of classical physics, specifically the laws of motion. Classical physics can predict the position of planets with great accuracy using the laws of motion. But these same laws could not predict the position and velocity of electrons. Experiments have proven that it is impossible to know both the precise location of an electron and its speed at the same time. Werner Heisenberg called this the uncertainty principle. The uncertainty principle has profound implications for modern science. It signaled the end of the notion of classical physics that everything in principle can be known and predicted, and ushered in the view that the universe is dynamic, changing, unpredictable, and in some instances, unknowable. By the 1920s, these ideas about the behavior of atoms and subatomic particles were developed into a new theory called quantum mechanics, or quantum theory. Since that time, physicists have learned much more about the subatomic world. It has been shown that there are three types of particles that are the building blocks of matter: quarks, leptons, and bosons. Protons and neutrons are made up of quarks, while electrons are leptons. Bosons are particles that carry discrete amounts of energy and interact with the four forces: electromagnetism, the strong and weak nuclear force, and gravity. These developments in quantum physics have had a huge impact on science and technology. They underlie our understanding of modern chemistry and biology and provide the theory for lasers, nuclear power, integrated circuits, television, and computers. Quantum theory focuses on the world of the infinitesimally small, but at about the same time that it was being developed, another theory was being formulated that explained large-scale phenomena. This theory was mostly developed by one man, Albert Einstein, and is called the theory of relativity. Many feel that it was the most important development in 20th century physics. Einstein developed his theory in two stages. The special theory of relativity was published in 1905, when he was only 26 years old. Special relativity links space and time into what Einstein called the space-time continuum. The three dimensions of geometry are length, width, and height, which give the coordinates of any position relative to a reference point. Einstein added the fourth dimension of time, because all events happen at some position at some time. This is not such a weird concept. The football player has to be not only at the right spot, but he must also be there at precisely the right time in order to catch the ball. He is operating in a four-dimensional world. Einstein believed that the motion of everything in the universe was relative, except for one thing: the speed of light in a vacuum. He came to a number of startling conclusions about space-time and the speed of light. His mathematical calculations determined that the faster an object moves, the more its mass increases, and in turn, it takes more and more energy to accelerate the object. As it approaches the speed of light, the object's mass approaches infinity, and it would take an infinite amount of energy to move it. Plus, time would come to a halt. Since this is impossible, Einstein concluded that light is the only thing that can travel at this speed. But the most startling conclusion reached by Einstein is that energy and mass are linked with the speed of light in E equals mc squared. E is energy, m stands for mass, c squared represents the speed of light times itself. What the formula says is that mass and energy are interchangeable, and because the speed of light is such an incredibly large number, a small amount of mass can be converted into an enormous amount of energy. The nuclear reactions in the sun are an example of the conversion of matter into energy. This is called fusion, and we have even learned to use the formula to convert matter into energy ourselves. The energy released by nuclear reactors and nuclear bombs are based on the formula E equals mc squared. It is called fission, the splitting of the atom. Einstein lived to see the nuclear age, and like the rest of us, it left him with a sense of both awe and fear. Einstein continued to work on relativity, and in 1915, he published his general theory of relativity, which deals with the effect of gravity on spacetime. Newtonian theory holds that a planet circles the sun because of the attraction of the mass of the objects, but Einstein said that was not what was happening. General relativity holds that the mass of a huge object, like the sun, distorts the spacetime around it. In effect, the mass curves or warps the spacetime around the sun into what is called a geodesic. A planet orbiting the sun travels in a straight line, following the geodesic shape, and orbits the sun. Einstein's revolutionary ideas have not only changed our understanding of energy and matter, but his general theory of relativity has made a major contribution in our understanding of the universe and its origins. In recent years, physicists and astronomers have cooperated to create a new science of cosmology, the study of the origins of the universe. When Einstein was doing his work on relativity, astronomers believed the universe was made up entirely of the Milky Way galaxy, of about 100 billion stars. Beyond that were gases and little else. In the 1920s, Edwin Hubble, an American astronomer working at the Mount Wilson Observatory in California, learned from observations that those gases in deep space were other galaxies, and that there were not just a few galaxies, but many of them. We now know there are billions of them, some as far as 10 billion light-years away. Hubble's observations led to an astonishing discovery. The space between the galaxies was expanding, and therefore the universe itself was expanding. Einstein had realized that his theory of general relativity predicted an expanding universe, but because it conflicted with the firm scientific belief held at the time that the universe was unchanging, he introduced a fudge factor so that he could conclude the universe was static. After Hubble published his findings about the expanding universe, Einstein called the fudge factor the biggest mistake of my life. Hubble's observations, coupled with the general theory of relativity, have led to the Big Bang theory, which is an explanation of the origins of the universe. The Big Bang theory is still in the realm of speculation, but there is an increasing amount of evidence that supports it. Scientists actually think that microwave background radiation that is coming from deepest space is a form of echo from the Big Bang. Essentially, what the theory says is that about 14 to 15 billion years ago, the universe and all matter and energy in it was infinitely dense and hot and took up zero space at a point called a singularity. The universe then exploded in the Big Bang. Cosmologists believe that the universe was formed in this instant along with all forms of matter and energy as well as space and time. With the Big Bang, the universe immediately began to expand outward at tremendous speed. As it expanded, it cooled, and the rate of expansion began to slow. Matter separated into a type of quark soup of seething quarks, leptons, bosons, and other elementary particles. Around the first tens of microseconds, quarks began to condense into protons and neutrons. By 1 second, the expansion caused the temperature to drop to about 1 billion degrees, and during the next 3 minutes, protons and neutrons combined, creating the first nuclei of hydrogen and helium. It took another 300,000 years before expansion brought the temperature down to a few thousand degrees, and the electrons were attracted to the nuclei to form atoms. The vast majority of the atoms, which formed at this time, were hydrogen and helium that have the simplest atomic structure. 1 billion years after the Big Bang, when the universe was only about 1/5 of the size it is today, gravity began to sweep matter into clusters of dense masses, which became galaxies. As the hydrogen atoms were forced closer and closer together with the pressure of gravity, they became hot, and fusion spontaneously began. Stars were born in this process, radiating light in the form of electromagnetic waves. In time, many of the stars began to die as they burned up all of their fuel. Some stars collapsed under their own gravity and exploded into supernovas, and their matter spewed out into space, forming new atoms, stars, and planets. The universe continues to expand, and as the galaxies move further and further apart, the universe continues to cool. Controversies about the origin of the universe and a variety of related issues remain at the forefront of physics today. One of the most tantalizing mysteries has to do with black holes. Einstein's general theory of relativity showed that the warping of space-time due to the mass of an object could bend light. Some physicists speculated that a collapsed star could have such incredible mass that the energy of the light it radiated would be used up trying to escape the gravitational force bending it back to the star. Others disputed this, saying that there was no clear evidence black holes existed. Stephen Hawking, the British astrophysicist, replied that even though no light can escape from them, there is evidence that stars in their vicinity are affected by their mass. He believes that there could be as many black holes in the universe as there are stars. In a startling recent study, astronomers have concluded that there is a black hole at the center of the Milky Way galaxy, and all of the other stars in the galaxy are orbiting around it. There is speculation that there are black holes at the center of every galaxy. But an even more fundamental controversy in physics has to do with the future of the universe. Will it continue to expand forever and finally die a cold death? Or will it expand to a certain point and then begin to contract? If it contracts, the cycle will be repeated. The universe will shrink to the size of an atom, and another singularity will occur, called the Big Crunch. The answer to this question has to do with the density of the universe. Recent calculations of all the matter that can be seen suggest that the density is not enough to draw the universe back together. But other physicists believe that there is matter that we cannot see, such as black holes, and we may never be able to calculate. These controversies continue, but one thing has been resolved. No longer do we view our universe as static and unchanging, running like a big clock. The eventual goal of science is to provide a single unified theory that describes the whole universe. But that theory must recognize that we live in a dynamic world of constant change, and there may always be things which we will never be able to completely explain. The planetary model is a term physicists use to describe classical physics. True or false? The inability to give the precise location and speed of electrons is called the three types of subatomic particles that are the building blocks of matter are called quarks, leptons, and bosons. True or false? There are four forces in nature, and physicists think there is a boson that relates to each one of them. True or false? Quantum physics is the basis of the theory that explains computers. True or false? The special theory of relativity deals with gravity. True or false? Special relativity theory links space and time into what Einstein called the general relativity describes gravity as the effect of distortions in the fabric of space-time. True or false? The explanation of the origins of the universe that has been developed by cosmologists is called the black holes are vacant spots in space. True or false?